Alright, let's finish up this section. So, what I want to point out is that direct comparison is tricky. So, for example, let's look at this sum. Okay, so if you write down some powers, or you write down some terms of this sum, you think n squared over n to the fourth minus n minus 1. You can certainly say that that's less than so you want to say that that looks like 1 over n squared. Okay, that's the idea, but n squared over n to the fourth minus n minus 1 is actually greater than 1 over n squared. So you can't directly compare these because this guy converges. And if you have something that's greater than a convergent sequence, you cannot conclude that it converges. So you can't directly compare these. So that's where the next test comes in, which is called limit comparison. Okay, here's the limit comparison test. Suppose a(n) and b(n) are positive. So this is a common requirement in these tests. So I'm assuming that the terms are positive, and this limit exists. So when I stack them up, I get an honest limit. Okay, then I have some cases. If L is bigger than 0, then a(n) converges if and only if b(n) does. Okay. If L is equal to infinity, and this sum converges, so does this sum. And the last case is if L is 0, and the larger sum converges, okay. So here's how you can remember this. Okay, if L is bigger than 0, then a(n) and b(n) are going to infinity at about the same rate. So in this case, you can think a(n) is approximately the same as b(n). Okay? If L is infinity, that means that AN is much larger. Okay? So that if it converges, then the smaller one must also converge. And if L is 0, then Bn is larger. And so if it converges, then so does AN. I think that's the easiest way to remember this test. So let's return to this question we started with. The question from up here. Okay, let's limit compare this. Okay, so direct comparison didn't work. We can limit compare it. So what we do is we stack these up. So let's write this guy divided by this guy. Okay, it looks complicated, but it's not bad. This is the limit as n goes to infinity. Multiply by the reciprocal and you get n to the 4 over n to the 4 minus n minus 1. This is 1. Okay? So we are in this case. So this is bigger than 0. So this is the first case. So you know that this guy that we're comparing to, you know that this guy converges by the p-test. Okay, in this case p is bigger than 1, p is 2, right? So I immediately get that so does the sum that I was working with. N squared over n to the 4th minus n minus 1. So I get that it converges by limit comparison. Okay, so the idea is you think of a simpler sequence that has the same behavior. You stack them up, and if you get something that's bigger than 0, say something finite, then this sum and this sum behave in exactly the same way. So if this guy converges, then this guy must also converge. Okay, so final example. So look at this sum. Okay, so you want to limit compare this. So you want to say, does this converge? So to limit compare, you can say 1 over square root of n squared plus 4. That behaves like 1 over the square root of n squared, which is 1 over n. So that's your guess for what you should compare to, right? Now if you do the limit, 1 over root n squared plus 4 divided by 1 over n, you get n divided by square root of n squared plus 4. Okay? This limit is 1. So the way to see that is to multiply the top and the bottom by 1 over n and simplify. What you'll get is 1, so that's a pretty straightforward Calc 1 type of problem. And you know that this sum diverges. Okay, we showed this in two ways. You can think of this as the p-test or a harmonic series. Okay, we showed that that diverged using the integral test as well. So because this guy diverges, so does this sum. So this guy diverges, so this guy must also diverge. So the answer to the question is no.